Hey folks, today's Thursday, March 19th, 2020. When you get to this point, you probably have just finished watching that TV Ontario video that was specifically on electromagnetism, and it gave you a lot of background in terms of what some of the aspects of electromagnetic forces and fields are all about. Those are very good videos. They're very old. Those go back to when I was in high school. But the best thing about those videos is it actually shows and demonstrates some of the concepts that are really hard to visualize otherwise, particularly the hand rules. So we will work through the hand rules eventually and get there. We're going to kind of skip over them when we get to the magnetic forces for now, which means it makes the workbook navigation a little bit tricky, but we'll give you guidance on that to get you through. So just to tie things in a little bit, off to the left there on the screen, you see that we have the Earth and we have the Earth's gravitational field around it. Remember, gravitational fields are always towards the center of the mass of the object which is producing the field. When a mass is brought into that field, a magnetic force now is applied on the mass which is brought into the field. So this is just the gravitational field. Likewise with electric fields, if we have a charge, and let's make that charge, just for argument's sake, negative. If we move that charge into that field, now an electric force is applied to the charge. Or if we bring it to this field, an electric force would be applied to the field. Since it was identified as negative, it would in this case attract in. If it was negative, in this case it would go out. So then we only have a force applied when an object is brought into a field. In terms of gravitational fields, it's a mass. In terms of electric fields, it's a charge. Now when it comes to magnetic fields, so on a typical old-fashioned bar magnet, you can see the direction of the field around here. First of all, if you go to the North Pole, what you see is the field goes away from the north and it comes towards the south. Then it curves around kind of funny, and it even goes around from north to south in the area up close. It curves around on the outsides because of, again, the nature of the interacting poles. Most of the time, though, when we start to consider these fields, it's going to be in a situation like this, where we have the north end of one magnet here and the south end of a different magnet over here. So let me tell you about a gentleman whose name was Bill Evans. Bill Evans was a tradesman in the community. He worked in many different places. He worked for many, many years at Milner. Finished his career by retiring, and he came and he helped to teach at the elite program for several years. Many trades. He was a millwright. He was a mechanic. He had some electrical background. And I'm going to talk about Bill a little bit because it's going to help us just with a couple of things. So Bill Evans, you won't find him in town right now because every year in the fall, he heads down to Arizona where he has a trailer set up there, and that's where he spends his winters. So what does Bill do? In the fall, he goes from the north to the south. So when you have two bar magnets like that, the direction of the magnetic field, which is symbolized by a capital letter B, with your absolute signs and your arrow, goes always from north and towards south. So it's Bill in the fall, the autumn, and Bill starts with B, capital B starts with B. And when we see our formulas, you're going to see an additional way that'll help you remember that. So that's your magnetic field. That's the magnetic field. So just like in the other cases when we had to bring an object into the field to actually have a force applied, we're going to look at this a couple of different ways. The first way, which is just sometimes used, which is to bring a magnetic compass needle into that field. So if we brought that magnetic compass needle, I'll draw it here in black, the north end of the magnet is going to point towards the south, and the south end is going to point towards the adjacent north end. So that would be one thing that we could do. We could put a little tiny magnet or a magnetic compass needle and place in that field and see the force applied to it. However, that's not what we're going to do most of the time. What we're going to do most of the time is actually bring a moving electric charge into that field. And you're going to see that through the movies, or you saw that through the movies, that it was Hans Christian Ørsted, good old-fashioned Dane from Denmark, who first realized there was a magnetic field produced around any moving charge. Stationary charge, no. So we could take a little electron. Let's take the electron from up here, and we could just place it in there. There's no force on it. Nothing happens. But if that instead was moving, and it was moving into that field, there would be a magnetic force applied to it. Now, the way that it's going to work in this case, if you looked at those hand rules, if this is an electron, it's negative. So negative particles, we use our left hand. Positive particles like alpha particles, positive ions, something we're going to learn about in Unit 4 called a positron. Any of those particles, you'd use your right hand. So what you do is you put your fingers in the direction of the field. So if all the lights were out and you had to go around the room, you would field for the table and the chairs and things with your fingers. So field with your fingers. In terms of force, the magnetic force, if you want to hit something without hurting your knuckles, you hit with an open palm. And that palm is where the force will come, the magnetic force. So fingers of the field. The palm of your hand is the force. And your thumb is the direction, in this case of the charge, but in this case specifically an electron, because we're using our left hand. This is called your third left hand rule. And we're going to get into this in a lot more depth later, so this is just an introduction. So if I did that, I'm going to place my fingers between pointing of my left hand from the north to the south, so they're going from the left-hand side towards the right-hand side of the smartboard right now, which you can't see. My thumb then is the direction of the charge. That has to point down. So I have to rotate my hand so that my palm is facing into, in this case, the smartboard, into the page, to the screen you're looking at. So the thumb's going towards the bottom of the screen. My fingers are going towards, from north to south, going towards the right-hand side, which means my palm is going into the smartboard. So that's the direction of the magnetic force. So what would happen to this electron as it comes down? As soon as it enters that magnetic field, it's actually going to start to curve in a circular motion into the smartboard. So it would actually, if the magnetic field is big enough, it'll start going around in a circle. And that's what they do in a cyclotron. So the cyclotron is found in your cell phone. That's how it generates microwaves or in a microwave oven. It circulates electrons with magnetic fields that way. So it's pretty common technology going on around us. We just actually don't see it, so we don't know it that well. But that was getting into the directions. We have to worry about that too much for today. We're just going to talk about in terms of solving magnetic force problems. And in terms of magnetic force problems, we have two formulas. The first one is Q, V, small letter v, B, where the Q is the charge of the charged particle, V is the speed of the charged particle, and B, as Bill, is the magnetic field. Now the charge is going to be measured in coulombs, The speed is got to be in meters per second. The magnetic field is in a unit called the Tesla, which is after a capital T. So this is one of the two formulas I said. So this one is going to be used when you have a charged particle moving, has to be moving, stationary, there's no magnetic field around it, in a magnetic field. Give you a second just to look at that. So our second formula, it's actually going to involve a conductor that's moved through a magnetic field. A conductor, like a piece of wire. So this gets back to Bill again. So when Bill was down at the elite programs, one of the things he was very good at teaching was the electrical component of the elite courses, especially for the grade 10s. So Bill again comes into play, where it's B, I, L, where the B again is the magnetic field, measured in Tesla. I is the current. That's measured in amps, or more correctly amperes, but we just always say amps. And L is the length of wire in the field. Might be a very long wire, but it's only the part which is actually in the field which counts in this formula. So it's going to be BIL, or Bill. Easy way to remember, because you're going to look at questions, go, which formula do I use for magnetic force? Do I use QVB or BIL? So you know that if it's got the Q, it's a charged particle, Q for charge. If it's Bill, well, Bill was the guy who taught electrical wiring down in Elite, so it's a wire moving through that field. So that's it for today for this video, folks. So make sure you've watched the TV Ontario videos. My first kind of real job where I got a paycheck was putting on TV Ontario videos back on the old reel-to-reel days, because I understood the technology. So I used to work as a substitute librarian and go in on evenings, put those into play. So that's it for now, folks. Have a good one. Stay well. Stay safe. Take care.